Good afternoon and thank you for being here. My name is Etienne Vaillant. I'm a first-year PhD student at Femto ST Institute in Besançon in France, and I'm going to present you my work on the phase noise measurements of aluminum nitride contour mode resonators. Those resonators have been fabricated at the Carnegie Mellon University by Gianluca Piazza and his team. So the outline of my presentation contains 4 parts. First, I'm going to give a quick introduction of my work and give you the general context of my research. Then I will present you the specifications of the aluminum nitride contour mode resonators. After that, I will present you the phase noise measurement system based on the carrier suppression technique and show you the results. Finally, I will conclude and talk about the perspective that I have. So a quick introduction. You all know that precise time is essential to precise navigation because historically navigation has been a major, a principal motivator in man's search for better clocks. Today, oscillators and clocks are widely used in a number of large diffusion and scientific applications, and frequency stability of a signal is a major issue in many fields of research and industry. The market of time bases is very important, and the performance limitations due to the intrinsic noise of the circuits are still not perfectly controlled. Indeed, oscillators are beginning to be faced with the inherent noise of the resonators, which limit performances. And this is a reason why it is necessary to measure and to give attention to the measurement of phase noise induced by the frequency fluctuations of the resonators. The miniaturization requirements for time and frequency systems are ever increasing. For example, for atomic clocks, microwaves, or for GNSS receivers in nanosatellites. And MEMS devices are by definition of very small size and fit perfectly into collective fabrication processes, which saves on volume, weight, and costs, and they benefit from mass production batch techniques and processes usually used for conventional integrated circuits. However, those devices still must be subjected to many improvements in order to achieve significant and reliable performances. This is why I've measured the phase noise of aluminum nitride contour mode resonators, which are represented here. Those resonators have been, as I said before, have been manufactured at the Carnegie Mellon University by Gianluca Piazza and his team. And the schematic representation is shown here. I've measured, for this work, I've measured a set of 4 different resonators, and the chip containing the resonator has been glued into a 16-pin TO8 package, and every resonator has been wire bonded on separate pins. So the principle of the device, how does it work? A conventional contour mode resonator is composed of an AIN plate, which is sandwiched between a bottom metal electrode, a bottom metal plate, and a patterned top electrode. When an AC signal is applied across the thickness of the device, a contour mode of vibration is excited, and thus lateral strain is induced in the direction of the finger width. Given the equivalent mass density and the Young's modulus of the material that forms the system, the center frequency of vibration can be set by the width of the AIN plate, and the other dimension is used to control the motional resistor and the static capacitance of the device. So here you can see a picture of the device that I've measured. And yes, I have to precise that the resonant frequencies of those devices is around 221 megahertz. So an important parameter that I've measured first is the unloaded quality factor of those devices. And to do that, I've just measured the impedance with an impedance analyzer. And here you can see the impedance plots in amplitude and phase of these devices. There are one letter for one device because, as I said, I've measured 4 of them. So LN, GI for the 4 devices. From these measurements, the motional parameters of the devices have been directly computed in the impedance analyzer. And you can see a motional resistance around 100 ohms for every resonator, and a loaded quality factor, which have been calculated according to this equation, around 3,000. And all the motional parameters have been estimated according to the equivalent circuit. So now that I have the unloaded quality factor, I was looking for the loaded quality factor, and before doing this, I had to stabilize the thermal fluctuations of the environment. To do that, the TO8 package has been inserted in an oven, like you can see here, in order to stabilize the temperature around 55 degrees C. But the purpose of this oven was not to get a turnover point, but really just to avoid environmental thermal fluctuations. As we saw before, the motional resistance is around 100 ohm, and as the impedance is matched upstream and downstream the oven, I wanted to adjust this matching at the input of the device of the resonator inside the oven. So here you can see it on this figure. And from this setup, the transfer function have been measured with a network analyzer. And you can see here the amplitude and the phase of this transfer function. But as I adjust the matching of the impedance, the measurement of this transfer function has been realized between the input and the output of the oven. This is why, consequently, every part and every cable inside the oven took part in the measurement. This is why I don't reach the 0 degree phase, but it's not really important, because the important parameter was the slope of the phase at the resonant frequency, which corresponds to the minimum of insertion loss around minus 15 dB. And from the slope of the phase at the resonant frequency, I've calculated the listen frequency and then the quality factor, the loaded quality factor, which is around 1200, which is pretty bad and still improvable. But it's for the best of the 4 resonators, it's around 1200. And the listen frequency around 90 to 100 kilohertz. So this setup has been used for the phase noise measurement, which I'm going to present here, which is based on the carrier suppression technique. So how does it work? Here is a picture of the device on the test, which is the resonator, but actually I should have replaced it by the oven, because as I said, it was this setup used for the measurement, but anyway, the principle is still the same. So how does it work? The general idea of this system consists in reducing the noise of the driving source as much as possible, leaving the noise of the device on the test. The carrier suppression is done right here in the splitter by a first stage where the signals of both ways are subtracted. More precisely, a part of the driving source is separated in 2 arms in order to drive the device on the test, before being recombined in this splitter and additionally and vectorially added with a 180 degree phase shift to realize the carrier suppression. After that, it's maybe easier to understand with this. So here you have the noise of the source and the noise of the source plus the noise of the device on the test. And then when the suppression is done, it still remains the noise of the device on the test. A high carrier suppression requires a fine adjustment of both amplitude and phase of the two signals. So to compensate the losses in the device on the test, an attenuator and a phase shifter are inserted in the second arm to be sure to have two symmetrical signals in the splitter. So after the resulting signal is highly amplified without saturation and before the classical phase detection with an FFT analyzer. So this phase detection here, you can see, is done with the amplified signal is mixed with the driving source, with the signal of the driving source in phase quadrature, and then it remains in blue, the noise of the device on the test. An important thing to know is the device, the DUT here can be either a resistor, allowing us to establish the resolution and the noise floor of the measurement system, or a resonator whose phase noise is sought. Moreover, the calibration of this measurement technique is done by injecting a sideband in one of the arms of the bridge. And this sideband simulates a known phase noise. And with this known phase noise, we can correct the results with a calibration factor, which is directly determined from the sideband that we injected. And just one word on the driving source. Here I've used a CSO, a cryogenic sapphire oscillator, which is an ultra-stable source at 1 gigahertz, and I divided it with a direct digital synthesizer, an AD9912, to get the appropriate frequency of the devices. So from this setup, from this measurement, here are a few results. In red, you can see the phase noise of one device, one AIN resonator, actually the best one. And in blue, it's the noise floor of the measurement system. We can see that clearly the noise floor of the measurement system is at least 10 dB below the noise of the device. And thanks to that, we can see the 1/f slope of the device, which we can see the 1/f slope of the device. And for a script L of f at 1 Hz from the carrier, we have a phase noise of minus 125 dBc per Hertz, so at 1 Hz from the carrier. I've summarized here the phase noise for the 4 different resonators, and a driving power for the resonator around 140 microwatts, which means around minus 8 to minus 9 dBm, something. And moreover, the filter slope in 1/f cube here is hidden under the noise floor of the measurement system. And because, as we saw it before, the listen frequency is around 90 to 100 kilohertz, which means here it's clearly under the noise floor of the measurement system. So that's why we don't see the 1/f cube plot here. From these measurements, it's possible to estimate the short-term stability of an equivalent oscillator using those resonators. This is what I've done here. So starting from the knowledge of the phase noise, it's possible to estimate the short-term stability of an equivalent oscillator. Here, it's simply the thermal noise floor, which is equal to FKT over P. And in the bandwidth of the resonator, the slope of the power spectral density of phase fluctuations is a slope in 1/f with a coefficient B minus 1. And for the oscillator, the associated oscillator, assuming that the only flicker noise source comes from the resonator, is a slope in f over 1 over f minus 3. F1 over f cubed, so f to the minus 3, with a coefficient b minus 3. I've summarized the results here. So the equivalent noise, the estimated noise of the equivalent oscillators. And for the best of the resonators, the noise with the estimated oscillator is around minus 20 dB radian squared per hertz. So after that, the sigma y has been estimated according to this equation, and has been found around 10 to the minus 9 to few 10 to the minus 10, which is approximately the same order of magnitude as usual TC oscillator TCXO. So this leads me to the conclusion and to give a few perspectives. I've summarized here the main values that I've obtained with these measurements, so the loaded quality factor, the script L of F, the phase noise, and the estimation of the oscillator performances. A few perspectives is first the optimization of the thermal stabilization of the devices under test, because as I said before, the oven that I used was only here to avoid environmental thermal fluctuations. And another way of improvement will be the impedance matching. Actually, I should have modified this final sentence, because during the poster sessions, I've been advised to intentionally mismatch the impedance to improve the measurement. So I'll have to look deeper into that. Right now, it's not perfectly clear in my head, so I have to look deeper into that, but that's something that I've been advised during the poster session, so I will look deeper into that. Well, so I really thank you for your attention, and if you have any question, I'll be happy to do my best to answer you.